Hello everyone, I'm honored to be invited to attend the International Conference on Cryptography and Information Security. My article was accepted. The title of my article is a multifactor certificateless authenticated key agreement protocol on ECC. My name is Tang, and the report is mainly divided into 5 parts, namely the research background, the basic knowledge, and our protocol, the security proof, and the summary. Let's start from explain the research background first. In a traditional public key cryptography, shorted to PKC, certificates are needed to assure users of the relationship between a public key and its corresponding private key holder's identity. This gives rise to problems in certificate management, including revocation, storage, and distribution. To address these issues, introduced the concept of identity-based encryption, IDPKC. A user's public key can be derived from their identity, for example, their name or email address, while their key is generated by a key generation center, the KGC. But then comes the new problems. The issue of the key escrow, because the key generation center knows all users' secret keys. In 2003, L. Riyami proposed certificateless public key cryptography, CL-PKC, to solve the key escrow problems. Many certificateless authentication key agreement protocols, which were shorted to CLAKA, using bilinear mapping on elliptic curves, have been proposed. However, the relative computational cost of bilinear operation pairs is about 3 times higher than scalar multiplication on elliptic curve groups. Therefore, pair-free protocols are more attractive in terms of efficiency. These protocols have encountered some security issues, and researchers proposed models to standardize the safety problem, many including the MBR module and the ECK module. Because the MBR module is more comprehensive and has higher security requirements than the ECK module, so we choose the MBR module in security proof. Due to various problems with single and double factor authenticated key exchange protocol, multifactor authenticated key exchange has gradually become a research hotspot. Compared with traditional authentication factors, biometric characteristics have advantages such as uniqueness, difficulty in guessing or cloning, difficulty in loss and forgery, which can provide more reliable protection for identity authentication. Therefore, many multi-factor authentication protocols, including biometrics, have been proposed. However, these existing multi-factor key exchange schemes are only used locally to unlock keys distributed by trusted third parties. Essentially, whoever owns the distributed key can impersonate the key's user. It cannot resist internal privilege attacks. There's very little research on certificateless key exchange schemes using multifactor authentication technology, and they all choose generate an authentication key by combining multiple authentication factors. It cannot achieve real multi-factor joint identity. And our article proposed a multi-factor certificateless key negotiation scheme. The communication entity can choose different identity authentication factors, which is more autonomous and flexible. The proposed scheme has low computational overhead without bilinear pairing operations, and has been proven to be secure under the MBR model. The second part of the report is an introduction to basic knowledge. Here is the list of the description of notations used in this article. And the symbol EFQ denotes an elliptic curve E over a finite field FQ, defined by an equation, and the computational Diffie-Hellman problem means give a generator P of a group G and gives the set of A scalar multiply P, B scalar multiply P for unknown A and B from the set. The task of the CDH problem is to compute the A times B and the scalar multiply P. The divisible computation Diffie-Hellman problem means give a generator P of the G and the AP, BP for the unknown A and B from the set. The task of the DCDH problem is to compute the modular inverse of A times B and the scalar multiply the P. There are two types of adversaries against a CLAKA protocol. The type 1 adversary A1 can query the user's secret value and even replace the user's public key, but cannot obtain the user's partial private key. The type 2 adversary can obtain the master secret key of the system and query the user's private key, but cannot obtain the user's secret value and cannot replace user's public key. The ability of two kinds of adversaries of A is simulated by some queries with the challenger C. A certificateless authentication key agreement protocol is said to be secure if it meets two conditions. Condition 1, in the presence of a benign adversary on, and both oracles always agree on the same session key, and this key is distributed uniformly at random. Condition 2, for any adversary, the advantage of the adversary is negligible. The third part of the report is the description of our protocol. The phase 1, initializing phase. The key generation center, KGC, selects an elliptic curve E and define over a prime field, and the curve has a second point group G of the prime order Q, and the P is the generator of the group G. Step 2, KGC chooses the master private key S from the set and computes the master public key P is equal to the S scalar multiply the P. Step 3. KGC choose two hash functions, h1 and h2 for some integer. And step 4. The KGC publishes the system parameters and secretly keeps the master key of S. Phase 2. The user registration phase. First, we set secret value. The user UI takes multiple identity authentication factors as his secret values. Our scheme takes PIN codes and biometric fingerprints. The scheme supports the use of multiple devices on jointly complete identity authentication. Here we use 3 mobile devices as examples for explanation. The user enter the PIN code we denote as lowercase c1 on mobile device 1. Enter the fingerprint and generate the C2 through fuzzy extraction. And compute the capital C1, capital C2 through the computation. And then the user send the information C1, C2, and IDI to the KGC. Then is the partial private key extract. The KGC, on receiving the information from the user, it checks the IDI and chooses at random RI from the set and computes the capital RI, CI, and WI. Then it computes the lambda I and C0. After all the computation, it sends the message WI, RI, and C0 to the user. And the lowercase C0 is the partial private key of the UI. Then is set public key. Let PKI is equal to WI. WI is kept in public and considered as the public key of the user with the identity IDI. Then it computes CI and lambda I and confirms equation is true if C0 multiply P is equal to RI plus lambda I multiply the P holes. The private key is valid if the equation holds and vice versa, and the user UI stores the value in mobile device 1. Then is the phase 3, the server registration phase. First of all, it sets secret value. The server with identity ID J picks randomly CJ from the set as his secret value and calculate the capital CJ and then submit the registration information to the KGC. Then is the partial private key extract. The KGC chooses at random RG from the set and computes the RG, ZJ, and WJ, lambda J, and PJ. After all the operations, it sends the registration information to the KGC. Then is set public key. Let the PKJ equal to WJ, and also WJ is kept in public and considered as the public key of the server with identity ID J. The server computes ZJ and lambda J and confirms equation is true if it's true and it kept the secret key on its device and stores the value. The phase 4 is the key agreement phase. The user UI offers his IDI in mobile device 1 and sends the information IDI C1, C2, RI, and lambda I to the server SJ. After receiving the message, the server SJ chooses at random the key VJ from the set and computes the TJ, then sends the information to the user UI. After receiving the message, the user chooses at random the key VI from the set and computes the TI. Then the user sends TI to the SJ, and the UI computes the M0 and sends it to the mobile device 2 and the mobile device 3. After receiving M0, the user offers his IDI and PIN code C1 on the mobile device 2 and calculate M1 and send M1 to the mobile device 1. After receiving the information M0, the user offers his identity IDI and biometric information on mobile device 3 and calculate the biometric feature extraction information C2 and calculate the M2, then send it to the mobile device 1. After receiving the information of M1 and M2, the user UI calculates MI1 and MI2 and MI3 on mobile device 1. Then the server SJ computes MJ1, MJ2, and MJ3 on its device. Thus they agreed essential keys for UI and SJ can be computed as SKIJ, and they are the same. The part 4 is the security proof. Lemma 1. If to prove the security of our protocol in the random oracle model, we treat the hash function H1 and H2 as two random oracles. For the security, the following lemmas and the theorems are provided. The lemma 1, if two oracles are matching, both of them will be accepted and will get the same sections. Get the same session key, which is distributed uniformly at random in the session key symbol space. And the proof is assuming that I and J are session participants. A is a benign adversary. I and J send a message to each other in full accordance with the protocol rules. We know if two oracles are matching, then both of them are accepted and have the same session key. Based on the random oracle machine H2, the session key are distributed uniformly, since VI and VJ in the protocol are randomly selected, and the M1, M2, and M3 are randomly generated. The lemma 2 is assuming that the DCDH problem is intractable. The advantage of a type 1 adversary A1 against our protocol is eligible. And the security proof will be accomplished through a series of queries, such as the H1 query, create query, the public key query. And due to timing constriction, it will not be stated here. The specific process is reflected in the full paper. And the lemma 3 is assuming that the CDH problem is intractable. The advantage of a type 2 adversary A2 against our protocol is negligible. And the proof process is similar to lemma 2 and will not be repeated. The part 5 is the summary. In this paper, we have proposed a multifactor certificateless authentication authentication key agreement protocol on elliptic curve, which avoids the limitation of the certificateless management and the key escrow. Based on the CDH and the CDH assumptions, the protocol's security is guaranteed under the MBR model. The scheme implements the multifactor joint participation in key negotiation, where the KGC does not need to participate. If a new user is added, there is no need to update the information of all registered entities. There are, however, a number of potential directions that we can expand this week. At present, it is still a theoretical stage and needs to be further implemented and try to reduce time and communication costs. And we intend to identify potential collaborators that can assist in the implementation of our protocol in a real-world setting. And that's all. Thank you for listening. That's all my presentation. Thank you.